In this video, we're going to apply our understanding of polynomials to the more complicated extended response style questions. There are two main types of extended response questions. The first are the families of function style questions, which focus around having some generic polynomial and you're required to find all the coefficients of that polynomial. The second are the maximum/minimum problems, which require you to find either the maximum or the minimum of a certain quantity. In the case of polynomials, this is usually volume or area. There's a lot of overlap with quadratics here, so this video in particular is just going to focus on the cubic side of things. For those who don't know me, my name is Chris Iannozoni. I used to work as an engineer for a defense company, and I've since left that to start a career in tutoring. I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. All families of functions questions give you a bunch of information about some polynomial, and it's your job to figure out what the rule of that polynomial is going to be. A big part of this type of question is to figure out what type of polynomial you're going to use. There are three choices. You could use the polynomial form, you could use a factorized form, or you could use a completed square form. The polynomial form is actually the hardest one to use, so where possible, we're going to ignore the use of it. Let's check some examples. In this example, we're told the inflection point of our cubic. Under these circumstances, the inflection point form is going to be the most appropriate because it allows us to use a single point to solve multiple coefficients. In this example, we have an inflection point at 3, -1. This means that our b term is going to be -3 and our c term is going to be -1. All we have to do now is solve for a. Solving for a is always done by subbing in an additional known point, which in this case will be the point 4, 1. Now that we've found all the coefficients, we're just going to sub them all into our inflection point form and then present the information. Sometimes you're given the x-intercepts of your function. Under these circumstances, the axes-intercept form, or the factorized form, is the best type of polynomial for this because once again, you can solve a bunch of coefficients very quickly. If we have an x-intercept at 1, that means that one of the terms must have been x minus 1. The same can be said for x-intercepts at 2 and 3. Meaning we have x minus 2 and x minus 3 as the remaining terms. Once again, all that's left is solving for a, which, as I mentioned earlier, is done by subbing in an additional known point. And having done that, once again, we just put it all together. In this case, we're going to use a slightly modified version of the axes-intercept form. We just have to make sure that we are squaring the term that gives us the turning point. So that's going to give us x minus 1 and x plus 2 all squared. And just like I mentioned from earlier, we're going to solve for a by subbing in the remaining point. Plug everything in, and that's our final answer. The worst case scenario is where you have 4 random points on the curve. This is always going to require a 4-way simultaneous equation with the polynomial form. Let's not worry too much, this will always be a CAS question, so we're going to use the CAS tools to help us. On the TI Inspire, the syntax is going to be menu, algebra, solve system of equations, and then once again solve system of equations. From there, you're just going to select the number of equations to be 4, and you're going to choose the variables a, b, c, d, or pretty much whatever you want to call them. All you do from there is just fill each slot with all those equations. On the Casio, it's located under the Math 1 menu. Just make sure that you press that button a bunch of times to get the 4 equations you need. Once you have the 4 solutions for those coefficients, you're just going to sub those coefficients back into the original polynomial form, and that's your answer. These kinds of questions require you to find either the maximum or the minimum of a certain quantity. To solve these types of questions, we'll use the following framework. Let's check an example. Firstly, we can't find the maximum of anything unless we have an equation that describes that thing. In this case, we're looking for a volume, so we're going to try and find an equation that describes the volume. Our sheet is starting out as rectangular, and we're cutting out these squares that each have a side length of x. It's good to have a quick visual to describe this. All we do from here is create our volume equation. The volume of any rectangular prism is length times width times height. The only problem here is that we're using 3 variables to describe the full equation, where ideally we would only have 1. To fix this issue, we need to create a set of equations that allows us to get all of these variables back to just being a single variable. The first thing we can do is look at the height. If you refer back to the picture, the height of the box is purely dictated by x, how deep you cut those boxes. If you struggle to visualize that, do that actually in real life. Take a sheet of paper, cut from the sides, and then fold it into a box. You'll see very quickly that the height of your box is dictated by how deep you cut those squares. Next, we can focus on the length. The original length of the sheet was 20 centimeters, but because we've cut 2 x's from either side of that, the new length of the box is therefore going to be 20 minus 2x. The same sort of thing can be said for the width, which started as 10 centimeters, but we're once again cutting out 2 x's from either side. All we do from here is substitute that into the volume equation, and what you'll see is that you've now gone from 3 variables down to just 1. So to summarize, step 1 was all about finding your equation purely in terms of one variable. Step 2 is about graphing that function. This is going to make life easier because it allows us to see the key features much more clearly. There is one important thing to consider here. When you create equations from extended response style questions like this, there is often a restriction on the domain that is inherent in these real life scenarios. The first natural one would be that volume cannot be negative. If volume is on our y-axis, then we need to make sure that anything below y equals 0 is cut out, because we can't have negative volume. The last thing we should look at is a restriction on x. Remember, x is the side length of the squares that we cut out from our original shape. Let's take a look at that picture again. If we look at the width of our rectangle, we only have 10 centimeters to work with. If I were to cut 5 centimeters either side of that width, we would have no width left, and therefore no box. If I tried to cut any more either side, I wouldn't be able to. I can't cut 6 centimeters from both sides of a 10 centimeter line. This gives us a maximum domain of 0 to 5 centimeters, or x is between 0 and 5. So, after considering all of these restrictions, our new graph is just going to be the first turning point between the axes intercepts. Now this is a very common shape for these types of questions. You can take pretty much everything I just said about restricting the domain and just chuck it out the window. 99% of cases are going to look exactly like this. The cubic's going to start at the origin and then stop at the first x-intercept after the origin. So if you take anything away from that explanation, just do that and you'll be fine in the vast majority of cases. Anyway, now that we have our graph, we move on to step 3, where we actually answer the question. So we're looking for maximum volume. And since volume is on our y-axis, we can very clearly see that the maximum volume is going to occur at that turning point. So our goal is to find that turning point. If you already know calculus, then you can find that turning point by finding the derivative of our function and then setting that derivative equal to 0, because all turning points have a gradient of 0. In this case, you have a quadratic. That's going to give you 2 solutions. Only one of them is going to fit inside the domain. All you do from there is sub that x coordinate into the original function, not the derivative, the original function, and then that'll be your final volume, because volume is on the y-axis. If you don't know calculus, then you have to rely on the CAS's graphing tools instead. On the TI Inspire, you're going to go through Menu, Analyze Graph, and then Max. And on the Casio, it's located under Analysis, Gsolve, Max. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.